Rutherford planned a special experiment in 1909 to verify the Thomson atomic model. No one expected this experiment to lead to the discovery of atomic nuclei or the development of surface analysis technology based on the experiment. Back in the day, Ernest Rutherford experimented with measuring the specific charge of the alpha particles. He did not hold a vacuum because he thought that the alpha particles were so heavy that the air would not affect the experiment. In contrast to this expectation, the phenomenon of alpha particle being scattered by the air inside the measuring instrument occurred continuously. The Thomson model was the most widely accepted atomic model at that time. This model describes an atom as an electron embedded in a large, positively charged particle. If the positive charges were uniformly distributed throughout the atom, as in the Thomson model, then the air molecules would not form a strong electric field. Further, this should not affect the experiment. However, the results were different. Under the suspicion that positive charges will be concentrated at one point, he conducted alpha particle permeation experiments for approximately 5 years from 1908 to 1913. In the experiment, alpha particles were sprayed on a thin golden film, and the alpha particles penetrating the film were observed on the surrounding fluorescent screen. These expectations were correct. If Thomson atomic model is correct, all the alpha particles should easily penetrate the thin gold film and be detected. However, among the alpha particles incident on the thin gold film were highly refracted, and alpha particles that bounced backward were also found. Based on the detected alpha particles, Rutherford proved through a logical explanation that positive charges are concentrated in a narrow area and that the location should be the center of the atom. In addition, a new model, called the Rutherford atomic model, was proposed in which electrons exist around the positive charge concentrated at the center of the atom. According to the Rutherford's experiment, alpha particles that scattered after collision have different energies and scattering yields depending on the material of the thin film and direction of scattering. Thin films can be analyzed using ion scattering spectroscopy. The greatest advantage of this method is its quantitative analysis. This is because scattered particles are always detected at the same energy and yield in a specific scattering direction when irradiating the alpha particles of the same energy and amount. The modern ion scattering spectrometer was developed to measure even minute variations in the energy of scattered particles, a further improvement over the Rutherford experiment that measured only the number of scattered particles. Ion scattering spectroscopy is classified into low, medium, and high energy ion scattering according to the incident ion energy, and the measurable depth and depth resolution differ depending on the energy range. Among them, medium energy ion scattering, or MEIS for short, has a measurement scope of approximately 20 nanometers and a depth resolution of approximately 2 angstroms for the atomic layer, which is remarkable. The MEIS provided by the HB solution is a time-of-flight analyzer and is called TOF-MEIS. TOF-MEIS consists of following components: an ion source that generates helium ions that are incident ions, a collimation lens that primarily focuses the ion beam, an acceleration tube to accelerate helium ions up to 100 kiloelectron volts, an E-cross-B filter that filters impurities other than helium ions, a pulsing module that generates pulse beams, a Faraday cup for accurate measurement of ion beam current, and an objective lens that focuses the ion beam on the sample, and generated pulse beams are incident on the sample on the manipulator. The MEIS spectrum is obtained by measuring the energy of the scattered particles from the sample using a TOF analyzer. Most ions that are incident on the sample penetrate the sample without being scattered. This is because the incident ions must collide with the sample nucleus to scatter. However, the interaction range owing to the electric force between the sample nucleus and the helium-ion nucleus is very short, therefore, collisions rarely occur. However, a considerably small number of incident ions collide with the nuclei present in the sample with a very low probability, resulting in scattering and significant energy loss. In addition, because of the very low probability of collision, the sample destruction is very small. Therefore, this can be classified as a non-destructive analysis method. The ratio of the energy scattered by the elastic collision between the incident particle and the nucleus of the sample can be expressed by the following equation. This is known as the kinematic factor and is determined by the mass fraction of the nuclei colliding with the incident particle and the scattering angle. After measuring the energy of the scattering particles by placing the detector at a well-defined scattering angle position and analyzing it using the kinematic factor value, the elements of the sample can be determined. This will enable to determine various elements within the sample. For example, in a sample comprising 3 elements, ions are scattered by each element, resulting in different energies, and each spectrum appears at a different position on in the energy spectrum. Most ions that are incident on the sample pass through without scattering. However, even if they did not collide, they pass through the medium with very weak electromagnetic interactions. Owing to these interactions, the incident ions lose energy and gradually become slower. The incident ions slow down in proportion to the number of atoms in the sample passed. This is called the stopping power. Because of the energy loss owing to weak interactions, the incident particles lose energy with a statistical deviation. This is called straggling. Stopping power and straggling vary depending on the elements of the samples, and are well known through various theories and databases. Therefore, by measuring the energy lost as the ion beam passes through the sample, the thickness of the thin film can be calculated based on the density and stopping power of the material. Let us observe how the scattering energy is determined when the incident particles scatter backward by considering the kinematic factor, stopping power, and straggling. When the incident particles collide with the nucleus in the surface atomic layer of the sample, the energy of the scattered particles is reduced by the kinematic factor ratio. The energy of the particles scattered from the deep layer rather than from the first atomic layer of the sample includes energy reduction by stopping power and energy dispersion by straggling. The figure simplifies the previous explanation. Particles scattered from the surface layer of the sample are green, those from the middle layer are red, and those from the deep layer are blue. If the same element is thickly distributed in the depth direction of the sample, the width of the spectrum increases, as indicated by the dotted line. These spectra are examples of the sample containing gold, silicon, and carbon discussed earlier. When the sample is thin, the spectrum becomes narrow, as shown by the solid line spectrum, and when the thickness of the sample increases, the spectrum becomes wider, as shown by the dotted line spectrum. Although elements of the same number exist in the sample, the larger the atomic number, the stronger is the repulsion of the incident particle, generating more scattering. Rutherford derived an equation expressing the probability of collision detection between the ion and the nucleus of the sample in a specific direction. This is called a differential scattering cross-section. This value increases as the atomic number of the target nucleus increases, incident energy decreases, and scattering angle decreases. Therefore, if the number of incident and scattering particles is precisely measured and the scattering cross-section information of each element is used, a quantitative analysis of each element can be performed. The number of scattered particles can be expressed with the following equation. The number of scattered particles is proportional to the scattering cross-section, solid angle of the detector, number of incident ions, and areal density of target elements in the sample. By measuring the number of scattered particles, the quantitative number of target elements in a unit area of a sample can be analyzed. Let's assume that the MEIS spectrum of a thin hafnium oxide film of 5 nanometers measured under specified conditions is the same as the black solid line spectrum. If the number of incident ions is doubled, the height of the spectrum is doubled. When the hafnium concentration is reduced from 33.3% to 16.65% while maintaining the same incident ion number, the height of the hafnium spectrum is reduced by half. When the thickness of a sample increases from 5 nanometers to 10 nanometers while maintaining the same composition, the hafnium spectrum doubles in width while maintaining its height. In conclusion, MEIS measurements can be used to perform quantitative analysis without a reference measurement. TOF-MEIS uses multiple detectors. The upper detector is used to measure random or channeling spectrum with backscattering experiment. The lower detector is mainly used to measure hydrogen using elastic recoil detection analysis. In short, it is called ERDA. A random spectrum is obtained when all atoms in the sample are exposed to an incident ion beam with the same probability. In this way, the compositional depth distribution can be analyzed. Because the atoms in an amorphous sample are randomly present within the medium, almost all the atoms are equally exposed to the incident ion beam at any angle. The random spectrum can be obtained by measuring it from any incident and scattering angle. In contrast, in crystal samples, the atoms are lined up side by side. Therefore, when viewed from a certain angle, all atoms except those in the surface atomic layer are hidden by the surface atoms. Therefore, a random spectrum cannot be obtained when irradiating the incident ions in this direction. However, even for crystal samples, the angles at which the atoms of the crystal can hide are limited to a few angles. Therefore, if the crystalline sample is continuously rotated at a certain angle, all atoms are exposed to the incident ions with the same probability. Thus, a random spectrum of the crystal sample can be obtained. MEIS K120 can acquire a random spectrum of a crystal sample at a desired position by continuously rotating using the X, Y, Z, and 3 rotation axes. Because the atoms of the crystal samples are lined up side by side, when viewed from a certain angle, all atoms except those in the surface atomic layer are hidden by the surface atoms. Therefore, when the incident beam is irradiated in the lattice direction of the crystal, it is scattered only from the surface atoms and atoms that are displaced from the crystal lattice, and the spectrum measured in this manner is called a channeling spectrum. Therefore, by measuring the channeling spectrum, the depth distribution of the elements that are displaced from the crystal lattice can be analyzed. Using channeling spectrum, the spectrum of the element overlapped with the substrate's spectrum can be clearly recognized by reducing the spectrum height of the substrate. In addition, the substitution ratio of a dopant can be obtained. For this, first, the total number of dopants is obtained through random spectrum measurement. Then, the number of interstitial dopant is analyzed by channeling analysis. By comparing the difference between the random spectrum and the channeling spectrum, crystallization on information of the sample, such as the substitution ratio, can be obtained. In the case of a crystal sample, when the lattice direction is toward the detector, atoms except those in the surface atomic layer are hidden behind the surface atomic layer and are not visible from the detector. Therefore, particles scattered by hidden atoms and flying towards the detector cannot reach the detector because they are blocked by other atoms. When the detector orientation deviates slightly from the crystal lattice orientation, the atoms beneath the surface atomic layer become visible. Consequently, the scattered particles can safely reach the detector. Measuring the scattering yield of scattering particles as a function of the angle near the lattice direction of the sample is called the blocking dip measurement. The scattering yield is the lowest where the detector orientation coincides with the lattice orientation. The scattering yield gradually increases as it deviates from this direction to form a dip called a blocking dip. Because this blocking dip indicates the lattice direction of the sample, the position of the blocking dip changes when the lattice constant is changed by strain. Therefore, the strain depth profile can be analyzed by measuring the blocking dips at their respective depths. MEIS analysis mainly uses backscatter measurements. ERDA or forward recoil scattering measurement for special purpose are also used. ERDA stands for Elastic Recoil Detection Analysis. This method detects target atoms recoiling directly at scattering angles of 90th or less via elastic collisions. This method can be used to measure atoms lighter than the incident ions that are not measured in backscattering experiments. Because recoil particles are also generated by elastic collision events, the surface energy is determined by the kinematic factor, Kerr. The scattering energy is reduced as a function of depth by the stopping power, and the recoil cross-section is already well known. This can be used to measure the quantitative compositional depth distribution of lightweight atoms. The light element recoil particles have a low scattering yield, and their energy is also lower than that of the scattered particles. Hence, they are buried in the other spectrum of the energy spectrum and are not easily visible. Therefore, additional tools, such as a mylar film, should be added to analyze recoil particles. In comparison, a light element recoil particle reaches the detector earlier than a scattered particle in TOF-MEIS. This is because the flight speed increases in inverse proportion to the square root of mass. Therefore, the recoil spectrum is naturally separated from scattered spectrum. If ERDA is measured by the TOF method using helium ions, recoiled hydrogen can be analyzed without a filter in the 20 nanometers thick region of the sample surface. Thus, this method has an excellent detection limit and depth resolution compared with other RBS type equipment. TOF-MEIS can analyze the composition and thickness of various samples. This spectrum is the silicon oxide thin film spectrum. and the marked area is the silicon region of silicon oxide. The height indicates the silicon composition ratio, and the width indicates the thickness of silicon oxide. These graphs show the MEIS spectra of silicon oxide produced by the thermal oxidation and CVD methods, respectively. The marked area is the silicon area of the thick silicon oxide. As shown in the graph, the silicon scattering yield of silicon oxide, the green spectrum produced by CVD, is lower than that of thermal oxide, which is the white spectrum. This means that the silicon composition ratio of silicon oxide produced by CVD is lower than that of thermal oxide. The silicon composition ratio of thermal oxide is 33.3%, whereas that of silicon oxide produced by CVD is 26.9%, which is lower. These spectra are examples of the MEIS analysis of high-K materials. The graph shows the spectra of ultrathin hafnium oxide films with thicknesses of 1, 3, 5, and 7 nanometers. The difference in the width of the spectrum is clearly visible, even with a thickness difference of only 2 nanometers. This graph shows two different hafnium silicates spectra. The compositions and thicknesses of the thin films can be analyzed. As shown in the purple graph, the hafnium concentration is higher, silicon concentration is lower, and thin film is thicker in the purple graph than in the green graph. This graph shows the spectra of a silicon germanium thin film with a thickness of about 20 nanometers. The composition ratio of silicon and germanium must be accurately determined because the bandgap of the silicon germanium thin film depends on it. By analyzing the height and width of the measured MEIS spectrum, the composition ratio and thickness of the silicon germanium thin film can be accurately analyzed. The fact that the spectra of the three silicon germanium thin films have different heights implies that the composition of each silicon germanium thin film is different. The measurement results show that the germanium concentration increases and the silicon concentration decreases in the order of purple, green, and blue spectrum. This graph shows the spectrum of silicon nitride. Using this spectrum, the composition and thickness of silicon and nitrogen can be analyzed. This spectrum lowered the spectrum of the silicon substrate using a channeling method to more clearly confirm the nitrogen spectrum. In addition, the ERDA spectrum of this silicon nitride sample was measured to analyze the hydrogen profile as well. By simultaneously analyzing the two preceding spectra, the depth distribution of the overall composition, including silicon, oxygen, carbon, nitrogen, and hydrogen could be obtained. This graph shows the MEIS spectrum of the indium gallium zinc oxide sample, called IGZO for short. It is a transparent oxide material comprising indium, gallium, zinc, and oxygen. The properties of IGZO can be modified by adjusting its composition and thickness. Therefore, an accurate analysis of the composition and thickness is important and can be achieved using MEIS measurements. These spectra are random spectra of the IGZO samples fabricated under various conditions. The composition and thickness of each spectrum can be obtained by analyzing the different heights and widths of the spectra. MEIS can measure compositional depth profiles not only as a single layer, but even when multiple stacks of nano-thin films are formed. This graph is the MEIS spectrum of a multilayer film in which 2 nanometers thick hafnium oxide and 3.5 nanometers thick silicon oxide are repeated 5 times. As can be observed from the graph, the analysis results indicate a clear distinction between the layers. Analytical methods using ion beam sputtering on multilayer ultrathin films cause severe compositional distortion at the interface owing to mixing and matrix effects. MEIS can be used to quantitatively analyze multilayered ultrathin films without distortion. This is because MEIS is a non-destructive technology that does not require sputtering. This sample is molybdenum disulfide, with a structure in which atomic layers with a sulfur-molybdenum-sulfur structure are repeated. When each atomic layer consists of a different element, peak separation is only allowed when the thickness resolution is on the order of angstroms. Performing MEIS measurements at a grazing angle maximizes the thickness resolution and allows separation of the molybdenum and sulfur spectra. This indicates that the thickness resolution of MEIS is equivalent to the level of the atomic layer. This spectrum is the TOF-ERDA spectrum of silicon nitride. At the surface, hydrogen concentration profiles in the range of about 20 nanometers were analyzed. This graph shows the hydrogen analysis results of the silicon oxide thick films manufactured by CVD under various conditions. The results show that the hydrogen concentration varies from 2% to 12%. MEIS can also measure 3D nanomaterials such as quantum dots and FinFET. The figure shows the TEM image and MEIS spectra of 3 types of cadmium selenide zinc sulfide core shell structured quantum dots. A 3-dimensional composition profile can be obtained through MEIS measurement and 3-dimensional analysis. MEIS uses the average signal from multiple quantum dots in a sample rather than a single quantum dot. This is because the size of the ion beam is considerably larger than that of one quantum dot. Therefore, all the quantum dots within the beam size of the ion beam are measured. This yields more representative results than that by the TEM analysis of a small area. This figure shows a schematic of a FinFET, a 3-dimensional transistor. FinFETs are fabricated by building a fin structure with a size of several nanometers, implanting dopants into the walls of fin, and then forming a gate on it. Because FinFETs have a 3-dimensional and regular geometry, the concentration of dopants in different regions can be measured using backscattering experiments performed in multiple directions. An experiment to measure the upper surface. An experiment to measure the upper and lower surfaces. And an experiment to measure the upper and the side surfaces were performed. Consequently, the structure of fin and 3D composition distribution of the dopant were analyzed through 3D analysis. These results were obtained from MEIS measurements of thin silver-copper alloy films. ICP-MS is known to be very quantitative, and the quantity measured by MEIS was verified to be the same as the result of ICP-MS within the error range. In other words, the MEIS results were highly quantitative. These graphs on the left show samples prepared by ALD of hafnium zirconium oxide and MEIS spectra and analysis results for samples whose thickness is controlled per cycle. As shown in the 2 graphs on the right, the number of ALD cycles and the quantities of hafnium and zirconium analyzed by MEIS are linearly proportional. In addition, in the case of the 0 cycle, their quantitative value would be 0. Therefore, an analytical technique in which the quantitative analysis result matches the certified amount of material or deposition cycle can be said to be quantitative. Therefore, MEIS is a quantitative technique to check any change in the 0 cycle estimation result even when the sample surface is contaminated. The same experiment was performed by changing the surface contamination level. After forming hafnium oxide ultrathin films with various thicknesses from 1 nanometers to 4 nanometers, The thickness of the carbon contamination layer was changed from 0.25 nanometers to 1.3 nanometers, and the zero cycle estimation result of hafnium was confirmed. The same experiment was performed using the XPS. The XPS results showed that zero cycle estimation results increased as the contamination layer thickness increased. Unlike XPS, MEIS had a zero cycle estimation result close to zero, irrespective of the thickness of the contamination layer. In conclusion, MEIS had better quantification characteristics than XPS when a surface contamination layer is present. These two graphs show the results of analyzing the same hafnium oxide sample with TOF-MEIS and RBS, respectively. The TOF-MEIS, as shown in the graph on the left, was able to analyze the composition and thickness changes in ultrathin films of a few nanometers. However, RBS uses an incident beam of 1000 kiloelectron volts on the same principle as MEIS and has a depth resolution of 10 nanometers or more. Therefore, only changes in hafnium quantification could be analyzed. In other words, the depth resolution of MEIS in ultrathin film measurement is about 2 angstroms. This is extremely good compared to that of RBS. In the past, the samples used were very thick, with a thickness on the order of several micrometers. This was sufficient for quantitative and thickness analyses with RBS, with a thickness resolution of 10 nanometers. However, currently, with the thickness of the sample becoming increasingly small, the demand for MEIS analysis is increasing. In summary, MEIS is a non-destructive method compared with other surface analysis techniques and has a considerably good depth resolution of up to 2 angstroms. In addition, an absolute quantitative analysis is possible without reference material measurements. Currently, HP Solution supplies MEIS K120, a system for laboratory, and has developed TOF-MEIS for measuring a 300 mm wafer. TOF-MEIS for a wafer measurement uses 30 micrometers focused ion beam to analyze samples in a semiconductor wafer test pattern using a non-destructive method. In the process of manufacturing semiconductors and displays, where the thickness of the products decreases, MEIS is the only solution that can quantitatively analyze the compositional depth distribution with a 2 angstroms resolution. Because of this, the demand for MEIS analysis is gradually increasing in the industry, and this will become an essential basic analysis technology for semiconductor and display process monitoring in the future.